Testing? Yeah, that's on. Good.
Well, I wanted the small ones though. Was the big ones for me?
Is it for Nikki?
There's just a lot of noises for me. Yeah, dude, they're always screaming.
Yeah, okay. I haven't started up yet. Rohit, you want to do the lights? Thanks, good. Okay, thanks. Okay, well, oh, afterwards. Oh, great. Okay, great. Great. That's the new one. Good. Great. Thank you. I bought a spare, by the way, the other day, an off model, not an Apple one.
Oh, okay. How is it?
I haven't used it much, but in case I get stuck, because I left one here the other day. Great. Thanks. Oh, great. Thanks a lot. Terrific. Thanks. Okay, let's get started. As you all know, Wednesday is the midterm. It's only got 5 problems. They're not bad. Remember to buy parts if you need, and when I hand out the exam on Wednesday, I'll point out a particular part. If you can't get it, you should come and buy it, because it'll help you with the next part. But I'll explain that when you get the exam. Also, be sure that none of the material in Chapter 3 will be included in the exam. I mentioned that in my announcements to you. Okay, so let's review what we had in Lecture 8. We're talking about general birth-death processes, looking at some special cases. We began by looking at a constant birth rate, which means this, and only births, there's no death. That led us to the famous Poisson process, and we found through our study that implied a constant birth rate. Yes, this birth rate did lead to the Poisson process, and it also implied that the inter-arrival time between arrivals or births was exponential. So that triplet is something you have to keep in mind. They're all equivalent. Then we went to a very simple case where we had a mentioned the general pure birth, which means rather than forcing all the birth rates to be the same, they could be arbitrary. We didn't take that very far, just mentioned that handles it. We can write down the equations. Third example is pure death, which means there's no births ever. Items only die. So we have to start somewhere. And as an example, we'll start, say, with probability 1. We'll start with n in the system, and it'll drop down to n minus 1, n minus 2 down to 0. And this, in fact, was the probability of finding k in the system at any time. And of course, you see it's dropping down with this quantity here. Then we went to a very special and important case, number 4, the birth-death system with constant parameters, which means all the births have the same rate, all the deaths have the same rate, and that led us to the famous MM1 queuing system. We haven't focused much on it, but we talked about it. This is the simplest, interesting queuing system, which means exponential inter-arrival times and exponential service times and first come, first serve. And we'll talk about some of its parameters in a little bit, but recognize that this fourth example is very important. We also pointed out, I took you through the torture of trying to find the time-dependent probabilities, and we got it. Some of it's in one of the homework examples, which I have not assigned because I feel kind to you, but you might want to look at it for the solutions. And it led to a bunch of Bessel functions. The whole point there being that time-dependent solutions are very hard to find, even for this simplest, interesting queuing system. There is work in it. It's always very hard. Now, we're going to take this particular case is a special case of this more general case, as it says, is a birth-death with arbitrary parameters, going back to the early case. And I'd like to study this because, in fact, last time we did look at that case. That was a system, birth-death only. You can't jump arbitrarily, just to nearest neighbors. The system for solving it is our pi q equals 0. It's a continuous time system, discrete state, continuous time. We need the sum of the probabilities to go to 1. And we're looking for the equilibrium probabilities, which is limited as t goes to infinity. It's probably finding x in a system time t equal to k as t goes to infinity, assuming there is a solution. And this is the state diagram we drew. We drew a circle around the kth state and used the inspection method to write down the balance equations. And so by inspection, if you look at the equation that comes from the red circle, it says rate in equals rate out in equilibrium, no growth in that once you're in equilibrium. This is the rate in from the state below, k minus 1, the state above, k plus 1. And this is the rate out from u. You're leaving at a birth rate and a death rate. And there's a special equation, this blue circle here, for the 0th state, which gives you this very simple equation. And we always need this. And with this set, we have enough to solve it. And so, in fact, we started to build it up with P0, P1, P2, and then guessed solution. And of course, our guess was correct. This is the guess we made. And we find it satisfies these equations. And because these ergodic Markov chains have unique solutions, once you have a solution that satisfies the equations, you've got the only solution. And here's the equation, which gives you the probability of having nobody in the system. And so that combination we ended last time at. That's a key equation. You should know it for the final exam and for most of your queuing work. It's extremely valuable and easy, and it applies for birth-death only. It basically says probability of finding is the product of the birth rates from 0 to k minus 1 divided by the death rates from 1 to k times p0. Shortly, we're going to choose a whole bunch of lambda k's and mu k's and show you many different queuing models for which this equation gives a solution. Okay, but the last thing I left you at was to say, when do you in fact get an equilibrium solution? So I believe we call this equation 19. Yes, let me identify that here as well, because we'll refer to it here and there. This is equation 19. And in fact, it's the principal equation for what I call baby queuing theory. Baby queuing theory basically is the application of this equation. Now, in order to have this equilibrium exist, remember there were various cases. There was recurrent non-null, those are the good case states. There was a recurrent null, those are not so good, and the transients also not so good. In order for this recurrent non-null system to occur, we simply need to say that we require that P0 be in fact greater than 0. Namely, occasionally the system has to empty, which means it gives breathing time for the server, so the queue doesn't continue to grow to infinity, which would not be a stable case. Occasionally it comes to 0. So intuitively this makes a lot of sense. But I want to put it in more precise terms. So let's define some things. I want to define a couple of sums. A sum called S1 and a sum called S2. S1 is defined to be the following. It's the sum from k equals 1 to infinity of the product of I equals 0 to k minus 1 of these ratios, lambda I over mu I plus 1. And I'm going to define this other sum, S2, to be the sum from 1 to infinity again on k times the product from 1 to k now on I of mu I over lambda I, the inverse. And you don't get an I plus 1, you just get an I. And here are the conclusions from those sums. Okay. All states of our birth-death process will be ergodic, which is what we want, if and only if S1 is less than infinity. That's the first statement. Second statement, all states will be recurrent null again, if and only if S1 is infinite and S2 is also infinite. And the third case, of course, all states will be transient if and only if S2 is less than infinity. Of course, the ergodic case is the one we want. But the others can exist, you want to be careful. Now, so let's talk about that a little more carefully. The ergodic case will give rise to a set of probabilities, P sub k, that we're looking for. That's the whole point. And that's the case of interest to us. And it's going to be true if the set lambda k over mu k remains less than 1 for some k and on beyond that k. I'll say that more carefully in just a moment now. i.e., if there exists a k0, some value for k, and some constant c, which is less than 1, such that for all k greater than k0, greater than equal to k0, we have the ratio lambda k over mu k less than equal to c, which itself, as you know, is less than 1. That's trying to be a little bit more careful. And the equilibrium argument we're using here for birth-death does, we'll see, apply beyond birth-death as well. Okay, so now let's focus again on the MM1 system. And let's use equation 19 now to solve it. What did we try to do for the MM1 system before? We tried to find the transient solution, and we struggled with it. And if you remember, I pointed out there was one term in the transient solution which was hinting to the equilibrium solution, and we're going to see that here. If you go back to my notes, I think it was last time we found that transient solution. But you're going to see it appear here. Okay? So just to get you in the mood of queuing systems, we have a queue, we have a server, we have customers coming in at a rate lambda from a Poisson process. They go into service. How long do they spend in service? An exponential amount of time at a rate mu, which means 1 over mu is the number of seconds they spend in service. So let me actually write this as 1 over mu. It'll be more meaningful to you. 1 over mu seconds in service from an exponential distribution. Namely, specifically, lambda k equals lambda for k equals 0, 1, etc. Mu k equals mu for k equals 1, 2, etc. Also, if we're talking about a queuing system, I should tell you that there's infinite queuing space, so the queue itself can get infinite. And we'll see later, we're talking about first come, first serve. I don't ordinarily say those things because it's implied if I don't say otherwise, but I want to focus on it here. And of course, we saw the state diagram for this. I'm going to draw it again. There's state 0, state 1, state 2, state k minus 1, k plus 1, ... And the transitions going up with births all have the same rate, namely lambda. Let's continue that picture. And going down, they all have the same rate mu. We've drawn this many times. But in this particular case, the parameters are, as I'm showing, strictly lambda and mu. Now, instead of writing down the balance equations, which I would do by the inspection method, and then trying to solve them, I've already got the solution. I showed it to you up here. It's equation 19. This line right here tells me what to do with those lambdas and mu's to find the pKs. So let's do exactly that. So now I don't have to even use the inspection method here. Okay? So I'm going to say plug into equation 19. And what are we going to get? P sub k equals P0 yet to be found times the product of birth rates divided by death rates, going from 0 up to k minus 1, of lambda sub k, which is lambda, of a mu I plus mu, lambda I, which is mu, lambda, over mu I plus 1, which is mu. And what is that? That's simply P0 lambda over mu to the k. And that's for k greater than or equal to 0. Now, let's check equilibrium, see if this is going to give us an equilibrium solution. Okay? Let's check. Let's check S1. S1 is the summation, k equals 1 to infinity, of the product I equals 0 to k minus 1, of lambda I over mu I plus 1. That's the condition. And what's that equal to? That's a summation on k from 1 to infinity of just lambda over mu to the k. And as long as lambda is less than mu, this will be less than 1. Certainly less than infinity, which is the requirement. So I'm saying this is true if lambda over mu less than 1. And we're going to hypothesize that's the case. Physically, it makes sense. The rate at which people are coming in is faster, is slower than they can be kicked out. If that was not the case, you'd get growth and you would not have an equilibrium. Now let's get P0. P0 can be found a number of ways. Let's use the equation. Okay? It's 1 over one plus the summation, k equals 1 to infinity, of the product I equals 0 to k minus 1. I'm writing down the general version here. Lambda I over mu I plus 1, which is simply 1 over 1 plus the summation of lambda over mu to the k, and that's going from 1 to infinity. And what is this sum I just wrote down? You've done this enough times in homework. Anybody? I'm hearing yes. Okay. So let's write that down. That's 1 over 1 plus lambda over mu over 1 minus lambda over mu. Okay? Well, that's what P0 is. So what does that all come out? Multiplied by 1 minus lambda over mu, you get 1 minus lambda over mu. That's P0. Now, if you recall, we've defined rho in the past to be the to be, the probability system is busy. So this thing, P0, is 1 minus the probability being empty. So rho is exactly lambda over mu. We've defined that before. So basically, we require, as we said, lambda over mu less than 1, which means 0 less than equal to rho less than 1 for ergodicity. So the solution for MM1, and by the way, you don't ordinarily have to check this S1 situation, because if rho is less than 1, you've got it. The answer here is that pk equals 1 minus rho, rho to the k, for all k. That's a critical thing for you to know. Anybody who's ever studied Q in theory can quote that for you. It's the distribution of number and system for MM1. That is the term I told you see in the transient solution. You saw 1 minus rho, rho to the k as a leading term times something else, which in turn went to 1, and all the rest dropped to 0. So there was a clue this could have been the equilibrium solution. And notice, by the way, that it is a geometric solution. Geometric distribution. What do we know about the geometric distribution? Does it have a property? Yes. Memoryless. It's the only discrete distribution that's memoryless, which means its tail looks like itself everywhere. So now we know the two. For continuous time, it's exponential. For discrete time, it's geometric. And notice, this MM1 system is just full of exponentials. And its solution is geometric. There's something very pleasing about that. Okay, maybe you don't find it pleasing. I don't know. Okay. Okay, now, let's go after something else now. This is very important. That's the distribution for number in system, MM1. Let's find the average number in system. I'm going to call that n bar. Average number in system. And by system, I'm including the server. Back to this picture again. It's the whole shebang. It's all of this. How many in that box? Well, how do we find that? I already know what pk is. That's just the average k, right? Summation of k, pk, from 0 to infinity. And that's clearly, I'll take the 1 minus rho out. I'm going to plug in the red equation. Summation k, rho to the k. You've seen that 100 times. You're going to play with that. You're going to take one of the rows out. 1 minus rho, take a row out. You got a summation of k rho to the k minus 1. What does that look like? It looks like the differential with respect to rho. You've done this in homework so many times. That's the partial with respect to rho of summation of rho to the k. And anybody remember what that turns out to be? Anybody tell me what that is? Yes. The whole thing is, that's what I was looking for, exactly. This bracket is 1 over 1 minus rho squared. You've seen that a few times already. And that's because it's this guy is basically 1 over 1 minus rho, differentiated, and you get 1 over 1 minus rho squared. So the solution to all of this is, believe it or not, rho over one of those, rho over 1 minus rho. Big result. Memorize it. Not so much for quizzes, but for your claiming to be an expert in queuing theory. Okay, and we're going to look at those things in just a moment. Now, it turns out that the variance, if you calculate that in the usual way, I won't take us through that now. The variance for this system in the number, so the variance of n is simply rho over 1 minus rho squared. And that's also worth remembering. Whoops. And by the way, the appearance of 1 minus rho squared occurs very often in variance terms in queuing theory. So let's look at some pictures now, okay? Let's see what this geometric looks like, and let's see what this average number looks like. So let me pull that up. Here we have the distribution for number in MM1. Okay, please note this is MM1. In this particular plot, if you looked at some of the numbers, if rho equals a half, a moderate number, geometric distribution, the tail always looks like itself. And for the average number in system, it's going to look like this. Keep making that mistake. And I'm plotting it versus rho, obviously. What is that function again? It's rho over 1 minus rho. And the important thing to note, as is true for any queuing system, by the way, is that as rho approaches 1, the average number in system blows up to infinity. And we know from the ergodic condition we have to stay away from rho equals 1, because that's the case where the system will never empty and the queue will grow to infinity. This behavior is very similar for most queuing systems, especially in the region when things get nasty. Okay. Now, we also know a very important result from queuing theory. It's called Little's result. And we're going to take advantage of that now. What the Little's result said, it says the average number in a queuing system is equal to the arrival rate times the average time in the system. That means if I want the mean response time, capital T, the average time in system, that's equal to n bar over lambda. N bar I know is rho over 1 minus rho. So that's rho over lambda 1 minus rho. But rho itself is lambda over mu, so this whole thing is 1 over mu over 1 minus rho. So let me write that down as a result you should remember. The mean time in an MM1 system is given with that expression. Now this is only MM1, but I will tell you that the picture I'm going to show you for this and for n bar is true for almost every queuing system with small variations. Let me throw that picture up and then I'll answer your question. It's a very important result. If you have different queuing systems, more general in some sense, you may get a curve like that, or you may get a curve like that, but they all blow up as rho goes to 1, and they'll all have this. What is the meaning of what I just circled there? That's the mean time you spend in the queuing system when the load is 0, when there's almost never anybody there. So when I happen to come in, what happens to me? There's nobody in the system. There's no queue. I go right into service. How long do I spend in service? The average service time, 1/mu. So my total time in system, 0 in queue, 1/mu in service, and that's where this number comes from. And that's basically true for any queuing system. If it's empty when I come in, and that'll be the case when rho is 0, I'm just going to spend my service time. In this case, we symbolize it by 1/mu. So these are very important results. There was a question. At 1. At 1. You have to stay away from 1. You have to be less than 1 to be finite. Okay, your mind is thinking of pure deterministic. Every second somebody arrives, they spend 1 second in system, they leave, that's 1 more second, another guy arrives at time 2, this guy leaves at time 3, comes in 3. That's deterministic thinking, and you're correct. For DD1, deterministic inter-arrival times, deterministic service times, you can live at rho equals 1. But this has fluctuations. The fluctuations are what gets you. And that's what makes queuing theory interesting. The fluctuations in the arrival process, fluctuations in the service process. Either one, you could. In this case, for sure, I said so right up here. When I defined this system, this implies exponential inter-arrival times, exponential service times. Birth, death, Poisson, exponential. So it's stochastic. So we're specifically talking about this system and none other. But these pictures, in fact, these two pictures, blowing up at 1 and behaving roughly like this is true for many other queuing systems. So that's why knowing these 3 equations, namely the distribution will change. This won't hold for other queuing systems. But the average number in system and the average time in system typically behave this way. The shape will change a little bit, but the overall badness at rho equals 1 behaves like that. And in fact, you can show that for the most general queuing system, which I'll warn you right now, say for example, is GG1, which means any inter-arrival times, any service time, that basically as rho goes to 1, the system behaves like, the mean response time behaves like something, I'll put a question mark here, over 1 minus rho. That's the dominant behavior. And this is called the heavy traffic situation. Rho goes to 1. So we're anticipating this. We'll get this to probably the last day of the class. Okay. So let's ask a little more since we're doing so well here, and since you're enjoying this so much. Okay. Let's find the probability that we find at least k in the system. Namely, that's the probability of having greater than equal to k in the system. Well, that's easy. That's a summation over I from k to infinity of p sub k, or in this case, p sub I. And that's equal to 1 minus rho summation from k to infinity of rho to the I. And I'm going to point to u again. What's that sum? Oh, yikes, yeah. rho to the k over 1 minus rho. Okay. So let's write that down. So this is equal to 1 minus rho. Remember, first term minus first missing the order as a common term. This thing times, as he said, rho to the k over 1 minus rho. So this probability of greater than or equal to k is simply rho to the k. A very simple result. Probably more than k in the system. At least k in the system is rho to the k. Now, let me draw my little queuing system again. And up here, I found the mean response time in the overall system. So what I did is I found the mean time here. And that mean time we called capital T. I also know that the mean time in service is 1 over mu, which means that I can identify the mean time in Q. And I'm going to give that a name. In fact, I think I gave you the symbol for that one time before. That'll be W, means waiting time. The mean time in Q, we're going to denote by the symbol W. Well, if T equals W plus 1 over mu, then how big is W? W is T minus 1 over mu, which is 1 over mu over 1 minus rho, we know that, minus 1 over mu. And so what do we get for W? How about rho over mu over 1 minus rho? Moreover, we can get that another way. Let's recognize that the average number in system which we found is the average number in Q. I'm defining this symbol as the average number in Q, plus the average number in service. And what's the average number in service? Well, let me write down a space here. Whatever that number is, I'll call it n sub s for the moment, Little's result works. So that's the arrival rate times the average time in service, which I happen to know, which is 1 over mu. So the average number in service is just rho. No surprise, that's the fraction of time the server is busy. It all makes intuitive sense. So n sub q is rho over 1 minus rho, which is n bar minus rho. And so I'll get this as rho squared over 1 minus rho as the average number in Q. Again, something that you may want to commit to memory and amaze your friends. All this for MM1. Now, if I know the average number in Q, let's use Little's result here again. Let's just play around with this again. Let's say that the average number in Q from Little's result is the arrival rate times the average time in Q, which I denoted as W. But I know that's equal to rho squared over 1 minus rho. We just found that. So W is equal to rho squared over lambda, which is rho over mu over 1 minus rho, which we found right up there. So it's all consistent, one would hope. Okay. Now, so much for MM1 for the moment. We'll get back to it later. We'll do a lot more with MM1. But I want to take another case now. So the case we just studied was MM1. let me call this, I'll put a big dot here. Let's take another case now. We have this wonderful equation, 19. Let's use it. So I'm going to create another system. I'm going to create something called discouraged arrivals. Now, as scientists, engineers, if I ask you, invent a model which would suggest that the busier the system, the slower the input rate. I mean, people get discouraged, that queue's too big, I'm not going to join it. So given that we have a lambda k to play with and a mu sub k to play with, choose lambda k and mu k to represent the fact that the more there are in the system, the slower is the arrival rate. Well, I'm going to give you the example because you could do it many ways. I'm going to choose it this way. It's going to be some number alpha over k plus 1. And that'll be for k equals 0, 1, etc. As k gets bigger, lambda k gets smaller. As the queue gets bigger, people get discouraged, they arrive at a slower rate. And I'll allow mu k to be consonant mu. And that's k equals 1, 2, etc. Good. Here's a new system. It has some physical meaning, but whatever it is, solve it. Quiz problem? No, but if it was, how would you find the probability of finding k in this system in equilibrium? Two ways. Give me one. Yes. And draw the state diagram using inspection. Let's do that, okay? So 0, 1, 2, again, k minus 1, k plus 1, etc. And let's make the diagram interesting. Okay, let's put some labels. Excuse me, some labels on this thing. Excuse me. Okay. When there's nobody in the system, all that can happen is there's an arrival. What's the rate at which the arrival occurs? Look at the top of the page. When k is 0, at what rate are people arriving? Thank you, alpha. When there's 1 in the system, at what rate are people arriving? K is 1, it's alpha over 2. When there's k minus 1 in the system, they're arriving at alpha over k. When there's k, it's alpha over k plus 1, etc. And mu is always the death rate. Now, as you suggested, I'll now use my inspection method. That's one way. I would draw a circle, say around this guy, balance flow, set up the equations, and solve it. If I didn't know equation 19, it's a difference equation, and I'll use some form of difference equation solution, possibly the Z transform, possibly guess it or whatever. But what's the other way to do it besides this lovely picture, which explains it all? Another method. I just told you what it is. Equation 19, okay? Somebody's already solved that for us. This is one way. Second way is this. Namely, I can write down P sub k immediately from equation 19. It's P0 times the product from I equals 0 to k minus 1 of lambda I. What is lambda I? It's alpha over k plus 1 over mu sub I plus 1, which is mu. And all that, when I take that product, I'm going to get the following. I'll get P0 times alpha over mu to the k and a 1 over k factorial. Done. Let's find P0. P0 will be 1 over 1 plus the sum from k equals 1 to infinity of alpha over mu to the k, 1 over k factorial. And can someone tell me what this is? And I won't ask you. No, I don't want to ask you because you'll know it. Anybody know what that is? Exponential. You learned that in high school, right? So that's e the alpha over mu, except one problem. It's missing the 0th term. And that term would have been a 1, so subtract it. Okay? So I do all of that. What is P0 going to be? E to the minus alpha over mu. So pk is what I had before, alpha over mu to the k over k factorial e to the minus alpha over mu. And that's for k equals 0, 1, etc. What does that look like? Recognize that function for pk? Starts with a P, a capital P. Poisson. That's Poisson distribution. Turns out that discouraged arrival that we cooked up is a Poisson distribution numbering system. Okay? So what is the average numbering system in this case? Because you know Poisson, it's basically simply alpha over mu. Let's use Little's result now. N bar equals lambda t. But now we got to be a little careful. What is lambda? Lambda is changing. Okay? So we got to figure it out. Okay?
Here's what I found.
Siri's talking to me, but she reminds me that we ran out of time. So I'll finish this after the break. So take a break. Good job. You turned it off so fast I didn't hear it. said, trying to find this average lambda, whatever that is, it's not clear because lambda is a function of lambda of k, but we do know this is the case. Just repeating what I said a moment ago. We know that rho is 1 minus probability of nobody in the system. We know P0, and so this is what the average lambda is. So let's now calculate what T is from this equation here. So T is equal to n bar over this lambda. But n bar we know is alpha over mu. We found that a moment ago. And lambda we just cooked up is mu 1 minus e to the minus lambda over mu. And that's what T is. You can put that mu downstairs, you get a mu squared. Okay? Let's find it another way. We could have found lambda as follows. This funny lambda is equal to the what? It's equal to the sum over all possible number in systems from 0 to infinity of the probability of finding k in the system, the fraction of time the system has k in the system, times the lambda k associated with that. So let's plug in this way. Okay, that'll be the sum of all possible numbers of pk, which we already know, that's alpha over mu to the k over k factorial, e to the minus lambda over mu, times lambda k, which is alpha over k plus 1. And doing a little bit of algebra, we'll get mu e to the minus lambda over mu, take all that stuff outside. And that's basically the sum from 0 to infinity of alpha over mu to the k plus 1. You see there's an alpha over, next to alpha over mu. I pulled the mu out. So it's alpha over mu to the k plus 1 over k plus 1 factorial. And what is that sum, anybody? That's an exponential. E to the lambda over mu minus 1, because when k is 0, we start with term number 1. So we add and subtract that 1. So what do I get out of all of this? I get mu times 1 minus e to the minus lambda over mu, which I had up here. So another way to get it. You have to get a little clever to figure these things out. Yes, question? Well, we know what rho is, probably being busy. 1 minus P0 is probably being idle. So 1 minus idle is probably being busy. So rho is 1 minus P0. Okay, and then why is P0 equal to e to the minus lambda alpha? I'm sorry, it's alpha. You're quite right. You're quite right. That should have been all over the place. Okay. And I can actually use the first minus the second. Right here. Here. Thank you. And so that's still consistent with the error in both places. Thank you. That's good. Okay. Good. We're doing well. We've used our special equation 19 for 2 cases, MM1 and discouraged arrivals. By the way, if you had to invent another discouraged arrival model instead of the one that I cooked up here, how else might you, there's many other ways you could do it. Anything where lambda k decreases with k. Well, think of one. There's a million of them. Right. Alpha over k plus 1 squared. Or how about an e to the minus k kind of thing? Anything that decreases with k. And put that in the denominator. Put that in the numerator. Okay. So here's a new case now. I want to study the system we've referred to before, namely M infinity. We have an infinite number of servers. Namely, that means that lambda k equals lambda. But mu k, well, let's see. all service times are exponentially distributed with the mean 1 over mu, if you will, a rate of mu. If nobody's in the system, at what rate are people leaving? 0. There's nobody there. If there's one person in the system, she's got her own server, she's leaving at a rate mu. If there's 2 people in there, they both got their own server. At what rate is the system pumping people out? 2 mu. 2 servers busy, each pumping at a rate mu. Okay? So what should mu k be? K mu. Again, k equals 0, 1, etc. And same up here. Now you can start with 1, it doesn't matter, but 0 does it as well. Now, I could do what you suggested before, which I could draw the state diagram, use the inspection method, and try to solve the equations, or a better way, which is what chapter 3 is all about, use equation 19. So I'm not even going to draw the state diagram, even though it's an interesting one. I'll draw a piece of it. Okay, why not? Suppose I got the state k plus 1, just a little piece of it. And I'll draw the state k as well, k minus 1. Okay. People are going up, births and deaths. At what rate are people arriving? Lambda. It says that right above where I'm drawing. If there are k in the system, at what rate are they dying? K mu. And it's from k plus 1, it's k plus 1 mu. So you can draw the rest of the diagram. Do the inspection method? No, let's use equation 19. So let's do that. That's the whole point of this chapter. So we want to write that pk equals p0 times the product from 0 to k plus 1, k minus 1, I'm sorry, of the arrival rate, which is lambda, over mu I plus 1, which is I plus 1 mu. Now this looks very much like discouraged arrivals. It's lambda over something over I plus 1 times something else. I left the mu out of this, by the way. That's the same as this expression up here, isn't it? So we already know the answer. But let's write it down again. That's equal to, basically, well, we know the solution. Let's write it down. It's e to the minus lambda over mu. This time it's a lambda. And 9 times the factorial, lambda over mu to the k over k factorial. Done. N bar is lambda over mu. And t, what's the mean response time in system? Everybody gets their own server. How long does anybody wait when they come in? How much? 1 over mu, a service time, right. Plenty of service to go around, okay? Now, what do you think the condition for stability is for this thing? How would you blow up the system? Well, everybody who comes in gets their own server. You can't saturate that system. You just need lambda over mu less than infinity. Not 1, but infinity, because everybody gets their own server. And you can check that with the S1 condition if you like. Okay. Now, I'm going to take a slight excursion and take advantage of the MM1. So I want to go back to the basic MM1 system again. Because there's something very significant from an engineering point of view that our equations are going to tell us. Okay? So let's remember that for this system, the mean response time is the average service time over 1 minus rho. Okay? I'm going to write that a slightly different way. I'm going to write that as rho over lambda over 1 minus rho. And if I plot that, I'll get a picture like this versus rho, and this point over here is x bar, and I've plotted capital T. And this point, of course, is rho equals 1. Now, we don't have grocery clerks serving customers in the computer network or in a computer system. We have communication channels sending bits through a communication link. So let's think of it that way, okay? Let's consider a communication channel. And let's assume it has a capacity of, say, capital C bits per second. A gigabit, a megabit, a kilobit, whatever. Okay? C bits per second. And what's getting served in a network? What flows through a network? Data. And how do you represent the data? Either in packets or blocks. What is it that's moving? It's bits. Bits come in, it says, ship me through the system. So let's consider, basically, I'm going to let this notion of 1 over mu be the average number of bits per message. Let's assume message is the basic item we're moving with. And to come back to what we've always done, x bar is the number of seconds it takes to serve somebody, okay? So how long would it take to serve a message of length 1 over mu bits going through a channel of c bits per second? Okay? Well, it's a number of bits per message, the average, times the number of seconds per bit, which happens to be basically seconds per message, which is what we're looking for. So I need 1 over mu c as the average service time for a message in seconds. That corresponds to what we've really been talking about. It's not a bakery store with a clerk behind the counter. It's a channel pumping bits through it, okay? So let's consider such a system. Let me draw a queue containing messages being served by a channel of capacity C. And messages are arriving. When their turn comes, they go into the channel and they get pumped out. So they're coming in at a rate lambda, messages per second. And let's assume the channel is of c bits per second, and we're going to use 1 over mu bits per message. Okay. Now, how long do you spend in the system? I'm going to denote it as follows. The time in this system is how long I spend in the interval I just identified. And that's capital T, the mean response time. And let's assume, because we know how to deal with it, that the arrival process is Poisson and the distribution of message length is exponential. So it's an MM1 system. Okay? I've just converted seconds of service and used bits per second and bits per message. Okay. Now, I want to consider a second system at the same time. So I'm going to draw this again. In fact, I'll copy it and cheat on you. There it is. But the difference is that this system, and I'll use red to indicate what's different, this system has twice the capacity. And this system has twice the input. Twice as many messages per second coming in, twice as many bits per second to transmit a message. So I'm going to call this first system as having a response time T1 for 1 lambda 1c versus T2 down here for twice the system. Okay. So I'm going to get a little more graphic with you. I've got a system. I've got a certain throughput or input. I've got a certain capacity. And when I pump this thing through the system, I get a certain response time. 3 hands. Throughput, capacity, response time. Now what I just did is I doubled the throughput, 2 lambda, and I doubled the capacity, 2c. The big question is, what happens to the response time? Intuitively, engineers, good guesses, could only do one of 3 things. Go up, stay the same, or go down. How many think it goes up? You got to vote. How many think it stays the same? How many think it goes down? No hands up? It goes down by a factor of 2. I'll prove it to you in just a moment. It's something that queuing theorists never knew. I happened to get this result. They never knew this. And what a terrific result. You scale things up by a factor of 1,000, a bigger network with more capacity, the response time drops by a factor of 1,000. And the reason queuing theorists never cared about this is because they thought of people behind grocery stores, clerks. And how fast can one person serve? You can do 1 second of service per second. That's all you can do. But a channel can do more if you scale its capacity. So it's an engineering consideration of considerable importance. Okay. So let's figure this out, okay? Okay, so what do we have? We have T from this equation up here. Yeah, right here. I want to focus on this version of T. Let's write that down here. In general, I've got T is equal to rho over lambda over 1 minus rho. Or T times 1 minus rho is equal to rho over lambda. Solve this for rho. Rho turns out simply to be lambda t over 1 plus lambda t. I'm sorry, 1 over t over lambda. Is that correct? Let me double check. No, it is lambda t, isn't it? It's got to be lambda t. Why did I suddenly conclude that, by the way? What made me so sure of that? I did a dimensional analysis. The dimensions of rho are dimensionless. So upstairs I got lambda t, which is dimensionless, it's number. Same down here. Okay, now, this is a rather important equation. And I'm going to show you what that means graphically. So let's draw a profile. And in the horizontal axis, I'm going to put lambda. And I'm going to put rho on the vertical axis. And it goes from 0 to 1, of course. With lambda, you can get as big as you like. Now, what does this function I boxed look like? When lambda, suppose you pick t. If lambda is 0, what is rho? 0. And as lambda gets bigger and bigger and bigger, what does this function up here become? It becomes 1. So it grows like this. That's for a particular t, say t equal to 10. Let's choose another t. You get a whole family of these things. They eventually go to 1, right? Now, let's consider the following. Suppose I want to choose for a particular t, see, take 10, 5, change colors. 10, 5, 3, 1, etc. If you pick t and hold it fixed, what happens as you climb up this curve? You're holding t constant, you're improving the efficiency, rho is improving, and you're increasing the throughput. So in that case, you basically have a constant t, and lambda is increasing, the throughput's increasing, and the efficiency is increasing. That's nice. But suppose I chose the following way to move in this plane. Suppose I move that way. What am I holding there? I'm holding rho constant. So this bottom line says rho is constant. But what's happening as I move here? The response time is dropping from 10 to 5 to 3 to 1. So decreasing response time. And what's happening to the throughput? It's increasing. Now, in another color, say blue, suppose I followed a line like that. Now what's happening? Response time is dropping from 10 to 5 to whatever. Efficiency is increasing. And response time is increasing. Wow, you're getting everything. Okay, so let's say that. T is improving. Lambda is increasing. And rho is improving, increasing, if you will. You can have it all. The only price you're paying when you're getting all of it is the other things are improving a little more slowly. Okay. As I pointed out, queuing theorists never knew this, but from an engineering point of view, a networking point of view, it's very important to know that. And just remember the three-handed argument, okay? You gain dramatically. And the reason that some of you said it won't change if you scale up throughput and response time, you said, well, the throughput and efficient throughput and efficiency, the response time, you think stays constant because that seems like a fair trade-off. Capacity and throughput. You're sort of doing things fairly. So you might think that the response time would say, but it doesn't, and here's the equation to prove it. Okay? So that's the little digression I wanted to make on this MM1. Okay. So let's come back to our game, namely that let's use our equation 19 on some more stuff, on some important stuff. Let's consider the system of MMM, not an infinite number of servers, but a finite number of servers. Only m of them, okay? So what do we have? We have that lambda k is constant at lambda. And what is mu k? At what rate are people leaving? Well, if there's only one person, it's at the rate mu. If there's two people, it's at the rate 2 mu, 3 mu, up to m mu. After m, if you have m plus 1 people, at what rate are people leaving? mu still. And one poor guy's in Q. So let's say that. You model that, this real system in this way. So you got the lambda, so mu k basically is k mu for 0 less than equal to k less than equal to m, and m mu for k greater than equal to m. Or if you will, is equal to the minimum of k mu and m mu. Now, guess what the ergodic condition would be here? Between lambda and the other parameters. Well, what's the rate at which the system can possibly exit people? mu. So they can come in almost that fast. So just have to have lambda less than mu. Or if you will, lambda mu less than 1. Okay. We can draw the state diagram and suffer with it, or we can use equation 19. Okay? Let's use equation 19. Let's write pk, and let's break it into two cases. Now, first case is going to k less than equal to m. And by the way, this particular model is an important one, this MMM case. So the first case is pk is going to be p0 product I equals 0 to k minus 1 of lambda I. And for k less than equal to m, what is mu I plus 1? It's I plus 1 mu. And that's equal to p0 lambda over mu to the k over k factorial. On the other hand, for k greater than or equal to m, we get locked in. So pk there, same equation, p0 product I equals 0 to k minus 1 lambda I over mu I plus 1 mu. And what's that equal to now? Well, in this case, what is I plus 1 mu when I is I'm sorry. I starts at m, but I'm going to play it a little differently. I'm going to mark it as the rest of the product. Let's run this first product, not up to k minus 1, but up to m minus 1. Sorry. Product from 0 to m minus 1. And the rest of the sum I need is from m up to k minus 1. But that's not a sum, that's a product. Sorry. And what do I put in the second part? The reason I put the I plus 1 mu here, because that's how mu sub I behaves, up to m minus 1. Beyond that, it plays like mu, so I got a lambda over mu here. And that turns out to be simply p0 times lambda over mu to the k. That comes right through. And by the way, this is not a lambda. This is a lambda I, but the lambda I is a lambda. So it's lambda over mu to the k. And I get two terms downstairs. I get an m factorial. That came from the first product. And the rest of it, I get an m to a power. How many? How many terms there are? K minus m. And we have that lambda over mu is less than equal to, so lambda over mu is rho. We define that. And we're going to get the following result, therefore, that pk equals two terms, a p0 yet to be found, times m rho to the k over k factorial. That's for k less than or equal to m. And it's equal to p0 times rho to the k m to the m over m factorial. And that's for k greater than or equal to m. And remember, rho that I've defined here, it's the expected number of busy servers. It's another interpretation. Before we said rho is equal to the probability of the server being busy, but there's a bunch of them. Rho in this case is interpreted as expected number of busy servers. Okay. Now if we go for P0 using equation 19 again, we get 1 over 1 plus two sums now. The sum from 1 to m minus 1 of m rho to the k over k factorial plus the sum from m up to k minus 1, well, I'm sorry, this goes all the way to infinity, of m rho to the k over m factorial m to the k minus m. And if you do little sums that you get here, you get the following. That this thing is equal to 1 over a sum that doesn't close from 0 to m minus 1 of m rho to the k over our friend k factorial plus something which did sum and it gave us m rho to the m over m factorial. I've done some of the summation in algebra for you, times 1 over 1 minus rho. Now this particular system represents a telephone system for a building. Here's a building. How many telephone lines does the telephone company give us leaving the building? I mean, how many telephone handsets are there? Thousands. We don't have thousands of lines leaving the building, though. We have a finite number. How many? M. And if they give you M, what's the probability that if you pick up a phone, you can't get a free line? You're stuck. Right now, when you pick up the phone, you almost always get a free line because the engineers have designed the building well. They know the arrival rate based on how many people are occupying the building. They provide the number of phone lines, so you won't end up with an unavailable line. So this is very important. So let's continue what we want here. Let's ask for the probability that an arriving customer must join the queue. Suppose when you pick it up, you don't get a line, you wait. That's basically the probability of queuing. And so the probability of queuing, from what we just studied, is simply the sum over all numbers in the system of finding m or more. This is going to be basically this piece of k. You're going to let k go from m to infinity. That's the probability at least m are busy when you come in. And we happen to know the form for that equation, for at least m. So that's the sum again from m to infinity. And what is the k there? That's the lower piece of this equation on top of the page. So it's P0, rho to the k, m to the m, over m factorial. Now I'm going to couple some things here to make it a little more delectable. That's going to be the sum, again, from m to infinity. And I'm going to force, still got the P0 to live with, but I'm going to create an m rho to the k, because I want to sum this baby. To do that, I have to give some stuff back. I've got an m factorial downstairs. I've got to give back an m to the k minus m. I already had the rho to the k. I only had m to the m. I need m to the k, so I give back k minus m. That's equal to, let's pull out what does not depend upon k, p0, m rho to the m over m factorial. What I'm left with is the sum from k equals m to infinity of rho to the k minus m. Anybody care to tell me what that sum is? Say it again. 1 over 1 minus rho. Exactly. Happily, we forced that. So let's now put in the P0, and I'm going to get the following expression. Upstairs, I get an m rho to the m. That comes from the P0. Over m factorial. Times 1 over 1 minus rho. And downstairs, I get a sum from k equals 0 to m minus 1. We're going to get two of these terms. M rho to the k over k factorial. That does not sum nicely. Plus what I told you before, it does sum nicely. I get an m rho to the m over m factorial, 1 over 1 minus rho. This is the probability that no telephone trunk is available to a customer in the case of a telephone application. This is known as Erlang's C formula, after A.K. Erlang, the father of queuing theory. It's denoted in the literature as capital C for C formula. The parameters are m, the number of trunks, and the individual arrival rate, lambda over mu. And telephone engineers use this all the time. Basically, if you give them lambda over mu, they have to choose an m, so this probability is very small. Okay, so let's actually do that. As good engineers, we have tables. And here is that C formula. What I have basically is lambda over mu on the horizontal axis. And I've got the probability of loss here. I picked up the wrong picture. I picked up another one of Erlang's. Let me get the right one. I'm sorry. That's the one I want. Got lambda over mu on the horizontal axis, and I have here the probability of queuing. That formula on top of the page. And these different lines are for different numbers of m. This, for example, is for m equals 1, m equals 2, m equals 3, etc. And what you do to enter this curve is you decide what's lambda over mu for this building. Lambda is the number of customers coming per second. 1 of mu is the average holding time. And suppose it turns out to be this value. So you go up here and you say, how much probability of Q and E are you willing to accept? Okay? You pick a number. Say it's this much. You can't read it, but suppose it's that much. Then you simply come across here and say, hey, how many lines do I need? I need that many lines, whatever that curve is. I can actually read it. It looks like it's 11. Done. Apply 11 lines to that building. Engineers, telephone engineers use this all the time. Has anybody ever studied heat engineering, something called the Moliere steam tables? No real engineers here, are there? Well, they get similar complicated equations, and they want to design the size of a duct, a heating duct. They go to a table like this. They know the input. The equations are horrible, but somebody's plotted it out with a computer and just plug in. So use tables like this. Okay. Okay, but let's go on now. I want to choose yet another system which is related to this. And by the way, I call Erlang the father of queuing theory. He did this work in the early 1900s. He was working for the Danish telephone company. This man was an engineer. He was not a mathematician. But he created this little birth-death model. He didn't know it was something called birth-death. He knew when people come in, you start occupying lines. People leave, you leave the lines. And he tried to make a model. And he made an engineer's approximation. We know it's exact now. People come in at a rate lambda, bup, bup, bup. They leave at a rate mu, 2 mu, 3 mu, etc. And he actually balanced the equation. He said, well, flow in, flow out, boom. He got the equations. He didn't have equation 19. He had your approach, which is the inspection method. And he probably, I don't know if he knew Z-transform, but he solved it. But the point is, an engineer put together this model. And so for years, this, as queuing theory began to evolve, it was the domain of telephone engineers. Because making the assumption that people arrive at a rate, at a Poisson process, is a very good assumption. Because each one of us arriving is a different arrival process. When you get a whole bunch of them together and they're independent, then it's a Poisson stream in the limit. So that's an excellent approximation. Exponential service, more or less. It was good enough. He did this until in the 1930s, the mathematicians saw these models and said, oh, we know what that is. It's a birth-death process. And the person who promoted that heavily is a name you probably never heard of, but you should have. William Feller, F-E-L-L-E-R. Anybody ever hear that name? Nobody? Never studied probability theory? He's got some wonderful books. Brilliant guy, but he's a mathematician. And he gave a firm foundation to the birth-death process. I'll show you his picture another time after the midterm. He gave rise to the underlying theory and promoted it properly. So what happened is queuing theory moved out of the hands of the engineers, yay, to the mathematicians, oh my God. And they went after transient solutions, more complicated systems. It wasn't clean like we have here. We have beautifully clean results here. And they developed until, I'm giving you a whole history here, until World War II. World War II, a whole field called operations research emerged. What was it about? It was about logistics, moving people around, troops around, equipment around, taking them onshore, offshore, with boats and ships and all the rest. And a whole theory of max flow min cut theorems, maximum network flow stuff, queuing theory, how to move people, linear programming, a whole bunch of that stuff came in. And so queuing theory now moved into the hands of the operations research guys. And then what happened in the late 50s and early 60s? Computers came along. And we said, queuing theory is the right tool to describe the performance of computer systems and communication networks. Why? What do you care about in a computer system? The throughput, the buffering, the response time, the efficiency. Well, those are all the things we're talking about. Lambda, mu, probabilities, etc. So it's just the right tool. So it's grown enormously in our life and your lifetime to become a dominant tool for understanding the way computer systems and computer networks behave. And I spent a lot of my career in the early 60s convincing these damn telephone engineers that it was useful for more than just telephones. Okay? And funny. Yes, go ahead. Yes. He didn't use it, Claude Shannon did not use this in his theory, but he certainly used Markov models all the time. So the mathematicians had produced that, and he was, in some real sense, a mathematician. He didn't need it for his communication theory. Okay, Laplace transform, for sure, that was all over the place. Excuse me? It was operations research, but the tools were there. And for computers, too. I mean, how do jobs flow through a system? Where do they get stuck? How big should the buffers be? Do they get full? Do they overflow? The whole idea of working sets and all. These are all random things that are moving around in some kind of a system. Well, how do they behave? You know, Shannon, as you know, was on my committee, too. He loved the stuff when I was showing it to him. And he picked it up like that. Okay, so we've run out of time. I'm sure I'll see all of you Wednesday on time. We have the exam then, and I'll explain a couple things as we hand it out. You can almost surely finish it well within the time.